So one of the things that we talked about was that in for ductile materials, they have enough energy to have energy restored in themselves, uh, due to plasticity. So how we analyze ductile materials is a little bit different how we analyze uh, brittle materials. Although we start with the same state of stress, the formulation and equations and the application of it to find your factor of safety at the end of the day may be slightly different. So let's see how we approach this problem. So let's consider just a case for ductile material. But before we do that, let's go a little bit back and just kind of review. We had the case, this is uh, the true fracture strain. And if it's bigger than 5%, what you're saying is that if this is sigma yield, right? This is sigma yield, then, and you can draw a line here, this value right here, that's 0.05. So we are saying if your strain is actually bigger than this, you're able to achieve that without a problem. Um, Sorry, this is ill. So if you are able to achieve that somewhere there, you are able to achieve that, um, and you can go beyond this value, then it is a ductile material. However, if you get to the point where this value is actually, you know, this is 0.05 and this is less than that, anything on this side, you're saying that failure occurred before, so therefore it has to be a brittle material. And so a couple of things that you kind of keep in mind when you're doing these problems. When I have, let's say, a structure, right? Let's say a simple plate, and I'm going to have this plate structure, and it's a long plate, and I apply a load P there on both sides, and I have a circle in the middle of the plate. What happens here is because it's a ductile material and has enough energy to redistribute the loads. So what happens with the flow pattern does something like this and continues. It does not create spikes. There's absolutely no spikes created in this model because it's a ductile material. If it was brittle material, then the behavior would have been very different, but then it creates sharp stresses. So in for ductile materials, typically your stress concentration factor is safe to take that equal to 1. Static, that is. So for ductile materials, for any case that we are working with, and if we are working for ductile materials, plus is a static load, we can safely say that take KTA equal to 1, take KTB equal to 1, take KTS equal to 1. So you don't have to consider stress concentration factors at all for a ductile material. Now, uh, ductile material, remember, only for static. A couple of comparisons between ductile and brittle. This we already talked about. And in yield, typically what you have is sigma yield, and sigma yield in compression may be close to sigma yield in tension, but may not necessarily always be the case. So if that was not the case for ductile material, you could say that the sigma yield I will use is just the average of both of them. However, when you go to the industry, different methods vary, and the industry actually treats this value separate, the compressive separate, and the tension separate. Okay, I will let that for each one of the companies to explain how they manage that. Um, So here in this case, you have sigma yield, and also you have sigma ultimate. As you can see, the curve looks something like this. So this is where this is your ultimate, and this is your sigma yield. So you can see you're going to have distinct values there. Okay, and it has to be governed by a yielding criteria more than anything else. Now, brittle materials, on the other hand, they just don't have yield, as we talked about. So they just come here and they just fracture. So the only thing that you have here is ultimate in compression and ultimate in tension. Those are the values that you have. And typically, ultimate in compression is way bigger than your ultimate in tension. That's for brittle materials. And usually governed by a fracture criteria. However, we are able to um, we are able to solve the problem by other means without having to go to fracture criteria, but we may have to do a linear fracture mechanics analysis as well. Okay, so a couple of things that you have to keep in mind for uh, static and ductile material. Okay, first of all, the highest stress fibers yield. Load is shared with the next fibers. Cold working is localized. The overall part does not see any damage unless ultimate strength is exceeded. So this is basically the case I was telling you. If I had an infinite plate, I had a long plate applied load P. What's happening with localized effect they are not big great. You don't have those localized effects because of plasticity zone, you have ability to redistribute your stresses. Okay, so stresses can be redistributed. Okay, stress concentration uh, effect is typically ignored, as I just mentioned. So therefore, if it's a ductile material, just take your stress concentration factors equal to 1. You don't have to go to the table at all. Even if you're asked, what is the solve this problem and find the stress concentration factor. It says ductile, and you know it's a ductile material, take it equal to 1. Okay, some examples of that can be aluminum is a very good example of a ductile material. So is steel. So those are some titanium sometimes as well, depending on the temperature. So those are very good examples. Now, I want you to consider this. I want you to think about this. I have a structure that is a three-dimensional case, right? It is a state of stress, has 6 unique stresses, as you know. So it has uh, SXX, YY, ZZ, XY, XZ, and YZ. And typically we end up with plane stress, as we mentioned. So we only end up typically with three unique stresses, right? Typically, that's what you end up with. Um, uh, Now, when we are doing the analysis, is in testing, you can test typically, you take a bar and you're taking that bar, you take a small bar and you do uniaxial stress where you keep applying the load, keep applying the load, keep applying the load, keep applying the load until boom, it breaks. And vice versa, you keep compressing the bar, compressing the bar, compressing the bar until it breaks. So the question is it possible to take a three-dimensional case, a three-dimensional load, and simplify it to a one-dimensional loading case? And the answer for that is yes. We can take a state of stress, a three-dimensional state of stress that is completely full, that you have sigma xx, tau xy, tau xz, yy, sigma yy, tau yz, and sigma zz. The idea is to take this whole stress and somehow come up with one single stress that I can use to check my failure. Okay, so remember that the goal in these problems, what it is. The goal of all these problems is nothing else to know if something is going to be safe or is not going to be safe. We want to see if we're going to have failure. And how do we know if something is going to have failure? Well, we remember um, we had two cases. First of all, don't forget what we started with. We have your ND, that's a design factor. Okay, that design factor is actually multiplied to your load. So your new load will be your design factor times that load. Your moment will be multiplied by the design factor times that load. Your torque will be the design factor multiplied by that load. Your shear will be the design factor multiplied by that load. That's the first thing you do in any problem. You take your design factor and you multiply with your loads, and these are now the new loads that you use for your entire analysis, okay? So typically, design factors, as I mentioned to you, in many problems, a standard design factor can be 1.1 to 1.2. So that's kind of standard. Just add that to the problem without even just that's what we do. Now, if you don't have nothing given, just put 1.1, or in many cases, taking be a very good justification, you can take this equal to 1. There has to be a good justification. Everything we do is so many uncertainties involved with that, that to take this equal to 1 is kind of odd, awkward. So, and it's hard to justify it. But if you can come up with a good justification, that's the only way you will take this equal to 1. Otherwise, you will take a design factor. Okay. Now, with that said, so you have the design factor, and we talked about that already. What we now have is we also have the factor of safety, right? So the factor of safety obviously is going to be the strength, the total strength of my material divided by my actual stress. Okay, so this is here the top can be maybe it can be yield in tension, uh, it can be yield in compression, it can be yield in shear, depending on the cases that we are working with. This stress can be equivalent stress that we will talk about what is the stress actually. It can be actually your sigma 1, it can be sigma 3, or it may be tau max. So the only reason we took a structure and we learned how to find your sigma 1, sigma 2, sigma 3, because they are very useful when you're doing when we are doing failure analysis. Okay, so as for an example, if I'm talking a case where uh, it, it, I'm working for the case of uh, compression is critical, right? If the case was compression was critical, and then I know that sigma 3 would be less than 0, right? So what I will do is I will say my factor of safety in this problem will be sigma yielding compression divided by sigma 3. Okay, and obviously this also has a minus sign involved with it, right? With this may be just to put some numbers, maybe this is minus 45 and this number is minus 15. So minus minus cancels out. You just end up with 45 over 15. So you just take the absolute value of these, okay, check positive numbers. And then, so it applies the same as before that I explained to you that when this is bigger than bigger than 1, it is safe. If it's equal to 0, we are onset of failure, but we haven't failed yet. Okay? It is still safe. It is still safe. Now, if it's less than 1, then basically your part failed. Okay? What happens if in the case that you're working with, what happens if in the case that you're working with, let's say, shear critical, right? We say shear critical. So if I'm working with the case of shear critical, then your factor of safety uh, will be SYS divided by tau max. Okay, so and we will learn how to find these values as we move along in our discussion here today. Okay, so this is important. So if it was tension critical, in the case it was tension, then you could say your factor of safety was equal to sigma yield in tension divided by maybe sigma 1, right? We're assuming that sigma 1 is actually bigger than 0. Okay, and then same property, this has to be bigger than same thing applies if it's bigger than 0 is safe, equal to bigger than 1 is safe, bigger than equal to 1 is onset of failure, and is less than 1, then it has failed. Okay, so now the question is, what are the theories that actually are used for these cases? Okay, the first theory that we will talk about uh, is the maximum shear stress theory. Also known as the Tresca criterion. Okay, so the theory consists in the following. We basically, what we want to do is we take your Mohr circle and we say we have your Mohr circle, so we know that we have this circle in the three-dimensional part, right? The general three-dimensional part, it looks like this. And I want this to actually equal to a one-dimensional specimen, okay? So what we do here is we find the tau max and we equate tau max to this. So this theory consists in the following. It says that tau max actually is going to equal to sigma 1 minus sigma 3, as we learned before, divided by 2. And I always put the absolute value to make sure you get positive value. So this is tau max. And then your sigma ys is equal to, in this case, is equal to 0.5 times sigma yield. Okay? Um, and this comes from, this is sigma yield divided by 2. And later we will learn other options that we get by using distortional energy as well, where we can also show that that maybe this can also be sigma yield divided by square root of 3, and that gives you 0.577 sigma yield. Okay, this is also very commonly used, and we use this a lot, especially we work with, later we work with, we design screws and springs. This number will be used a lot, but this is way more accurate than this is way conservative in our approach. So basically what we are saying is the maximum shear stress theory, what it's saying is, given a state of stress, given a problem, you can basically say that your tau maximum that I know, I know my tau maximum. Uh, then if I divide this and I take my factor safety now, and uh, and I divide this by my sigma yield in shear, that has to, again, the same properties, has to be bigger than 1 or equal than 1. So this is onset of failure. This is safe, and less than 1, this is failed. Okay. So this is what the theory actually consists in. And remember that this tau maximum already has your design factor integrated into it. Okay. Why? This comes from your big state of stress. Okay. Just remember, you're finding a state of stress. And from the state of stress, you find what your principal stresses are, right? We always do that. We go ahead and we find your principal stresses. And we also find your overall tau maximum. Okay? And then in this particular case, remember how we calculated this, right? Each one of these quantities, each one of these guys is calculated based on the loads, right? So you have certain loads, okay, that actually produce this. And these loads, as I mentioned, they already are multiplied by your design factor. Okay, they are multiplied by the design factor that's already given in the problem. So that's already embedded inside the problem. Other alternative that many people use is I will apply this at the end, then I will keep this at 1.15, but that's a little bit more confusing. So this is a clear cut. This is the way we will encourage everyone to do in this course. Okay, that's the theory number 1. The theory number 2 is the distortional energy theory. Or maybe you know this as von Mises stress, von Mises theory as well. So basically, this particular theory consists in finding an equivalent stress, okay? And your equivalent stress will be nothing else than the square root of sigma 1 squared minus 3 times sigma 2. These are the stress invariants that we found last time. If you're working in the case of plane stress, and if it was the case of plane stress, then you can show that this theory actually gives you sigma 1, sigma 3 plus sigma 3 squared. Okay. Now, if we only have sigma xx and we have a tau, then let's say tau x or xy, then this equals to sigma xx squared plus 3 times tau xy squared. And if instead of tau xy you had xz, then just put xz. Doesn't really matter. So this equation becomes very handy and very easy to use. This equation actually what's going to end up is the whole derivation of that is based on this produces to you a ellipse, and your ellipse looks something like this. Okay, if you were to plot this, this is the ellipse, and this is what it will look like. And what we are really doing here is this line is the line of pure shear. This is the line of pure tension. Okay, so if you're across, so it's an ellipse that's rotated, and as you can see, sigma yield, minus sigma yield, minus sigma yield. This is assuming that sigma, you're using the sigma yield average for this problem. So if in the case that you had two different values of sigma in tension and sigma in compression, this is how you will do this. What's one thing nice when if you were to find, okay, if I want to find if factor safety, your factor safety will be sigma yield divided by sigma equivalent. And that's as simple as it is. Now we want to use the tensile stress. Why? Because this comes from a tensile theory. Okay, so that's what this theory says. Now let's compare. We have one more theory. Let me go over that theory very quick before we do any comparison. And we have what we call the ductile column Moore theory. Okay, and the theory consists in the following. If I make two circles, right, and they all end up here, and this one ends up there, then I can construct a line and say this is going to be my failure region. So I have a region here, I have a region there, it's a 90 degrees. Now I also have a region here that will be a 90 degrees. So basically, this is going to give you this failure region, and anything inside this failure region, I will be safe. Okay? So I want to talk about that in a minute, but you can see that if you did, for the case of maximum normal stress theory, I'm talking shear stress theory, this gave you something like this, because he was assuming that this value was minus tensile yield, and this value was minus tensile yield. You're assuming that there's actually the same value, which for ductile material is a very good approximation, but maybe a case in which you have these values that are completely different. Okay, so in that case, this is the region that you have, and this is the region that you work with. So if that was the case, then your theory is slightly different. Okay, and this is the stresses that you have. So you will have sigma 1 divided by tensile minus sigma 3 divided by sigma compression. And you can see that just use the absolute values there, right? And it has to be subtracted. Has to be less than 1 over factor of safety. Okay, so this is how this theory works. And if this theory, if this particular theory, if these were identically the same, then you would basically get the same value. You would get the same value as your maximum shear stress theory. Okay. Let's go understand how this really works. Let's suppose I got these 3 points, point A, point B, point C, and point D, okay? And I'm asking you which point is safe and which point is not according to each one of the theories, okay? So let's start with the maximum shear stress theory. Maximum shear stress theory. So for the maximum shear stress theory, is this dotted and darker shaded line region inside here? What can you say about point A? Well, point A is definitely safe. Why? It's inside this region. Okay, so there's nothing else there. Is the origin. So your factor of safety will be the point A minus the origin divided by what is available. What do you have available? What you have available is this is your factor. The total amount available is actually safe. So you have actually this approach is to infinite. Why? This is actually equal to what you have available. Okay, your strength available is anything on this line, the loading line, up to C. Okay, this is how much you have available. And A to 0, A is actually at A, so I don't have any distance, so that is 0. So that gives you the total strength divided by 0 gives you infinite. So let's say your factor safety is infinite. Anything bigger than 1, you are safe. Okay. So and then if I go to point B is also safe. I can see that it's safe immediately by the figures inside this region. Anything inside the region is safe. Okay. How do I really know this? Because I can say this is my total available. Okay. I want you to think if I have a bag. In the bag I have 20 apples, right? It is safe to say if somebody wants 10 apples, I can grab 10 apples and give them 10 apples because I have 20 apples available. If somebody wants 20 apples, I can take my entire bag and take the 20 apples and give 20 apples to somebody. However, if somebody's asking for 22 apples, I cannot give them 22 apples because my bag doesn't have 22. So 22 becomes the strength, the maximum possible load capability that your structure can have. Okay, so that is what we are actually trying to do here. We are saying this is the maximum available. Okay, for the maximum shear stress theory, AC is maximum strength available. That's the way you need to see it. Okay? So that's why I say my factor of safety will be the maximum strength I have available divided by my point B and the origin. The origin is nothing else than my point A. Okay, so that is going to be bigger than 0, as you can see, because this distance is smaller than this one. Got it? Okay. So let's go with point that we are still working maximum shear stress theory. Let's go with point C. Now at point C, this is what happens. At point C, it is still safe, but it's at onset of failure. It's about to fail, but it hasn't failed yet. And what you can see is your factor of safety is the total strength available, that's AC, divided by the everything that I'm using is AC. Okay, so actually it's equal to 1. So your onset of failure. Okay, if I use point B now, what happens at point D? Point D, the maximum is failed. First of all, you know it's failed because it's outside the region. C is safe because it's on the line, it's still safe. It's just about to fail. Then point D is outside the region. Since it is outside the region, then it has failed. But mathematically, if I was going to calculate that, the maximum I have available is A to C, and I have AD, but this line is bigger. You can see it, right? It's bigger. So therefore, this is going to be less than 1. So definitely it has failed. Okay? So let's see now what happens if I go with the distortion energy. Okay? For my distortional energy, the maximum I have available is AD. Remember, this is my distortional energy line. So this is maximum I have available. Okay? So this is max strength available. Okay? So again, point A is inside the region, so it is safe. But if you want to calculate your factor safety, that would be maximum available, and A to the origin, that is actually going to give you infinite. So it's bigger than 1, so it's safe. Point B, it is inside the region, so it is going to be safe as well. And if I put a factor of safety, the factor of safety will be A, the maximum available divided by AB, and that's going to be bigger than 1. I have more available than what I'm actually using. The same example of the apples. Maybe now I have 23 apples since I was 20. So I can give a couple more apples available. Okay. Let me continue right here at point C. It is also safe. It's not onset of failure for DE because my DE is the online is on this line. Okay. Not on this line. This is for my distortion energy, this one. Okay. So it is safe. And you can see that my maximum available is AD divided by AC, which will actually be bigger than 1. I'm sorry, not bigger than 0. This is all bigger than 1. 1. Make sure I got them right. Sorry, this is all bigger than 1. If you see a 0, just change it to 1, please. It's all 1. Okay. And then if I go to point D, what happens at point D? Point D, now I have the maximum, it is onset of failure. It is still safe. It hasn't failed, but it's at onset of failure. It's about to fail. So if I had this case, then your factor of safety will be AD divided by AD, and you can see that it's going to get equal to 1. So if you think about this problem now, which of these two theories is the most conservative one? Which one is the most conservative one? Well, the theory maximum shear stress theory is the most conservative. It's the most conservative one. Why? Because I want you to think about this. If I had 23 apples, somebody's only asking me for 20. Okay? I'm going to still have 3 apples in my pocket. So in this case, somebody's saying, no, you need to carry 23 apples wherever you go. So now you have a heavier bag because somebody decided to say you need to have extra 3 apples just to be safe. Maybe somebody's apples go rotten and you need to replace them. So you need to have those 3 apples. So conservative in the sense that which of my bags is more lighter. Okay, and what happens is in aerospace structures is basically we don't like heavy stuff. We don't want nothing to be heavy. We want everything to be very, 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 very light. So in most of the machinery, you might say, I don't care, but more material is equal to more money and more cost. And cost is equal to more material, more cost, and more less profits. And the companies don't like that. We want to create profit. We want to create structures that are strong enough, but we don't want to bulk them up just for the sake of bulking them up. We have to design them for a reason. Now, so that's why I said this is the most conservative one, because the one that's going to give you the highest is the one that's going to give you the highest size. Okay, so this one gives you the highest sizing. And if you're finding loads, it's going to give you the lowest load possible. Okay. Okay. Uh, so we talked about three theories, and you have a MATLAB code that actually does runs this very nicely. You have the MATLAB code that does this really nicely. Uh, and most of this stuff, I want you to do it by hand and in MATLAB. And where you go here is you go into theory, failure theory, and the code that you're going to run is failure theories. Okay, that's the code that you want to open up, and that's the code you want to run. So when you run this code actually does all three cases. So let me just run this. And again, as usual, the way we run MATLAB is press, uh, you want to just run it there, press this play button. Now let's answer questions. Just give me a sec. Okay. Let's suppose you're okay in inches. I'm going to make up numbers here. Let's suppose this is 1.25. What do you know? Let's suppose I know stresses, just to put numbers there. Minus 25. Um, this is 0. Let's put, there's no vertical load. Let's suppose I do have a torch. I have 0 here. I don't have vertical load. Let's suppose I do have a torsional load of 40. Making numbers up just to show you how it works. What type of material you're working? We are working ductile material. Let's suppose I'm working with aluminum. Aluminum has a yield of approximately 30 ksi. Let's suppose it is very close. Let's just for the sake of this example is 33, and Young's modulus is 30,000 ksi, and you're going to run the whole thing, and your code runs it. Okay, and what you're going to see is it created a file called Ductile Material. That file gives you a plot, and you cannot really see it, but it actually gives you the load line and gives you the design point that has to be probably just jammed up on top of this. Tells you where your design point is. Um, and uh, and what you can see is how all these theories actually are blending together, right? This is your Colomb-Moore, ductile Colomb-Moore theory, and this is your the red one is maximum shear stress theory, and this is your ductile, your distortional energy theory. Okay, so when you are actually when you do this, you're gonna see the load line is saying this is mainly a shear, pure shear. It's acting like shear. If you're on this side, it's acting like if it's in tension, a pure tension. And also the code gives you, if you go into failure theories, this is the output that tells you everything that you entered, okay? And your entire code does all the calculation. If you're using the case of stresses, it is assuming that the stresses you are giving already has the design factor multiplied, embedded into it, okay? And then you have another output called ductile, and then the ductile basically tells you, doesn't even ask you for the stress concentration factors because it has to be one. It calculates the modular resilience, uh, and is equal to that value. And then basically it tells you what your state of stresses are after applying your stress concentration factors, okay, which is actually, and also it multiplies the design factor. Um, so then you come here, you find your principal stresses, your maximum shear, and this is your failure. And what you can see is that it calculates all these ratios that it needs. The first thing you want to do a pure check on what happens on just pure tension and compression. And it says that this failed. So this, you may have to handle this very carefully. That means that if you're working in a case where it has pure tension, it's going to fail. So this is probably not a very good design. The von Mises stress is 88.6. Um, and then your factor of safety is equal to 0.36. So you can see distortion energy also said this has failed. And you can tell that, right? Because your dot is outside here, is outside the circle. Since I'm over here and I'm outside the circle, then obviously your design has actually failed. Then when you come here, you do your uh, overall shear stress, and then you also see this also failed. You column more, you evaluate column more, you also get this failed, and you plus the and does the plotting. So this basically concludes your discussion on failure theories for ductile materials.